In this video, we're going to talk about the idea of a maximal ideal. So here's a definition. Let R be a commutative ring with unity. And let I be a proper ideal of R. So in other words, I is an ideal, but not equal to all of R. All right? Then here's what it means to say that I is maximal. Then I is a maximal ideal of R if the following is true. If J is an ideal of R, such that I is contained in J and J is contained in R, then J is either I or R. Okay, so here's why we call that the condition for a maximal ideal. Here's a picture. So suppose this is my ring, and then suppose that I is an ideal. Then when we say that I is a maximal ideal, what we mean is that we can't find some other ideal that's still a proper ideal of R, but also properly contains I. So if we say that I is maximal, here's something that cannot happen. We couldn't have some other ideal, J, of which I is a proper subset, but J is also a proper ideal of R. So in other words, if you're another ideal, you have to be either I or all of R. Note that R is itself an ideal because R is closed under addition and absorbs multiplication in R. Okay, so that's an idea of what it means to be a maximal ideal, is that you're an ideal of R, you're a proper ideal, but there's no other ideal between you and the entire ring. Okay, so here's an example. This really could do with an example. The integers are a perfectly good commutative ring with unity, and the ideals of Z are those of the form principal ideal generated by n, which is the set of all multiples of n, for all n in the integers. Okay, so for example, this is an ideal of Z, this is an ideal of Z, this is also an ideal, although this is just the set containing 0. This is an ideal, although this is really the set of all integers because everything in the integers is a multiple of 1. So those are some examples of ideals. And it turns out this is a theorem. We're not going to prove it right now, but actually every ideal of the integers is expressible in this way. Every ideal in the integers is a principal ideal. That's not something that's always true. Not always is it the case that every ideal is principal, but we'll talk about that more later. But anyway, what I want to talk about right now is what are the maximal ideals? Which ideals are maximal? So here's one example, and I'm not claiming this is an example of a maximal ideal, it's just an example of an ideal, and we'll decide whether it's maximal. Let's take the ideal generated by 10, which is the set of all multiples of 10, all 10x where x is an integer. Okay? So in other words, 0 plus or minus 10, plus or minus 20, plus or minus 30, and so on. So the question is, if we're trying to decide whether this is maximal, the question is, can we think of some other ideal that's not all of the integers, but properly contains all of the multiples of 10? So some other ideal that's bigger than this, has all the multiples of 10, and has something else, but not the entire ring. And you may realize, well, actually there are a couple. For example, we could take the ideal generated by 5. That's an ideal. It contains all the multiples of 10, and it's not the entire ring of integers. We could also take the ideal generated by 2, and that would be another option. The ideal generated by 2 is the set of all even numbers, and that certainly contains all multiples of 10. So the ideal generated by 10 is not maximal, but let's suppose I take either one of these. Let's start with the ideal of even integers. Okay, is this maximal? Well, let's think about it. I already have all the even integers in here. So if I want to expand this and get a larger ideal, I'm going to have to include some odd number. So let's just imagine I take this and I stick on some odd number. Let's say I put on some k, where k is odd. Well, if I do that, then here's what's going to happen. K is going to be expressible in the form 2q plus 1 because that's what it means to be odd. And this is already in my ideal. Okay, so let's call my new ideal I. I is going to be the ideal that contains all of these and also k. Okay, so this is in I because I'm assuming that I contains all of the even numbers. And k is in I. So this means that 1 also has to belong to I because 1 is equal to k minus 2q, and that's the difference between two elements of I. Well, if 1 is in I and I absorbs multiplication, then that means that every multiple of 1 has to belong to I for every x and z. So that means that every x and z has to belong to I, which means I ends up being all of the integers, not what I want. So in other words, if I try to expand this ideal at all, the ideal generated by 2, I just end up getting all of the integers. That means that this ideal really is maximal. Okay, what about the ideal generated by 5? Turns out that one is also maximal. And the idea is kind of the same thing, although it's a little bit more complicated in this case. If I try to stick on anything else, so create a larger ideal, I should call it J really, because in the definition it's called J. So let's say J contains all the multiples of 5 and something else. And just so we have an example to play with, let's say that something else is like 7. Okay, it doesn't have to be 7. I'm just saying this is a possibility. Well, if J contains 5 and all the multiples of 5 and also 7, then let's just think about what that forces us into. Well, that means that J also contains 7 minus 5 because J has to be a subring closed under addition and subtraction, which means 2 also belongs to J. But now once 2 belongs to J, that means that 5 minus any multiple of 2 belongs to J because, well, if 2 belongs to J, then so does any multiple of 2. That includes 4. And 5 minus 4 also belongs to J, which means 1 belongs to J. And now we're right back where we were before, where once 1 belongs to J, everything belongs to J. Okay, now that was just for if the something else was 7, but if the something else is, well, something else besides 7, you could run the same argument using a little bit of number theory. So it turns out this is also a maximal ideal. Okay, and actually this is a fact. We're not going to prove it right now because I want to actually do something else with this idea of maximal ideals, but this is a theorem. The subgroup generated by n, which is an ideal of z, this is maximal if and only if n is a prime number. Okay, now that's actually a little bit imprecise. I really should say if and only if the absolute value of n is a prime number, because I could take the subgroup, or the ideal generated by -5, and that would be the same as the ideal generated by 5. But customarily we call an integer prime only if it's a positive integer. But anyway, that's a theorem about maximal ideals of the integers.